So welcome to the component around spectroscopy, how we analyze compounds to make sure we've actually made the compound that we think we have. And there's two sections, an SL component and an HL component. Today we're focusing on the SL component, spectroscopic identification of organic compounds. So in the end of the unit, you should have an understanding of the concept of the degree of unsaturation or index of hydrogen deficiency, an understanding of mass spectroscopy, NMR and infrared spectroscopy, and you should be able to determine the index for hydrogen deficiency for particular molecules and deduce from information the structural features of certain compounds using mass spectroscopy, proton NMR and infrared. The first thing I'm going to look at is the electromagnetic spectrum, which is also in your data booklet. So the EMS, which you probably looked at physics as well, interacts with compounds in ways that help identify them. And the ones we're going to be focusing on today are infrared spectroscopy, nuclear magnetic resonance, and also, just infrared spectroscopy and nuclear magnetic resonance. Okay? I'm going to link that to hydrogen deficiency and mass spectroscopy later, so you can actually work out the structure, purity, and composition of an unknown substance. So the energy for electromagnetic radiation, capital E, is related to the frequency V of the radiation by Planck's equation, which you see there, E equals hV, which equals hc divided by the wavelength, where of course h is Planck's constant, which is 6.63 times 10 to the negative 34 joule seconds, which is also given in your data booklet. E is the energy of radiation, measured in joules, and V is the frequency of the radiation, which is measured in hertz. The C is the speed of light, which is given again in your data booklet as 3 times 10 to the 8 meters per second. And lambda is the wavelength, which is of course measured in meters. So from this relationship, it can be seen that the energy is directly proportional to the frequency and inversely proportional to the wavelength. Okay? So E is proportional to V, and E is also proportional to 1 over the wavelength. So various regions of the electromagnetic spectrum are used in spectroscopy, X-rays, UV light, but the ones we're going to be focusing on are infrared and radio waves. Unlike ultraviolet and visible radiation, infrared radiation does not have sufficient energy to result in electronic transitions, but can cause molecular vibrations, which result from the vibration of certain groups of molecules about their bonds. Hence, using this type of spectroscopy, various functional groups can be identified in a molecule. The vibrational transitions correspond to definite and definitive energy levels. And the basis of IR spectroscopy is the spring model, which we will look at in the next slide. So, in the spring model, every covalent bond is considered a spring. Such a spring can be stretched both symmetrically and asymmetrically, as we saw in the last slide, bent or twisted, giving rise to a distortion. The force required to cause the vibration is based on Hooke's law from physics, and that is given as F is proportional to the displacement. Okay, and that can also basically give a constant in there, so it will be summarized as force is going to be the negative displacement times a particular constant depending on the strength of the spring, a constant of proportionality, where F is the restoring force, K is the spring constant, and X is the displacement. And we see that here in this wonderful GIF. So, the fundamental frequency of vibration V is based on a system obeying Hooke's law and can be related to the mass m by the following expression, which I'm going to put here. Okay, so V equals 1 over 2 pi, the square root of K over M. So that means that lighter atoms have higher frequencies. Stronger bond entropies also give higher frequencies. And heavier atoms will vibrate, of course, with lower frequencies, V. The same applies for multiple bonds, for example, double or triple bonds. If you imagine two atoms connected by a spring, the stronger the bond connecting the two atoms, the tighter the string. Okay, so the higher the spring constant, and therefore more energy will be required to stretch it. For a diatomic molecule, such as hydrogen chloride, only one form of molecular vibration is possible, that is stretching. So different molecules absorb at different frequencies because the energy required to execute a vibration will depend on the bond enthalpy. Infrared absorptions are typically cited as the reciprocal of the wavelength. This is known as the wave number and has the units of reciprocal centimeters. So for polyatomic species, there may be several different modes of vibration. For example, the water molecule has 3 modes of vibration: asymmetric stretch, an asymmetric stretch, and a symmetric bend. Okay, so we'll just put that there. So we've got, there we go. So you have a symmetric stretch, okay, an asymmetric stretch, and a symmetric bend. Okay, so they're bending like that. So this is the infrared spectrum of ethanol. So as you can see, the OH stretch comes in quite high energy at 3,391 reciprocal centimeters. Then comes CH stretches and the corresponding CO stretches. Okay, and essentially this is what you would see of a spectrum. So you have the percentage transmittance, okay, and they range between 0 and 100%, and this way the functional groups can be identified. The characteristic ranges of infrared absorptions of various bonds in different classes of molecules and different functional groups are given in your data book. For example, the carbon-carbon double bond of alkenes typically occurs around 1620 to 1680 reciprocal centimeters. So in terms of looking at this particular spectrum of ethanol, note the following: a strong broad peak in the region of 2,500 to 3,300, characteristic of the OH of the alcohol. A strong peak in the region of 1,055, 1,100, which is correspondent to the fingerprint region of the infrared spectrum, where complex vibrations like the CO stretches are seen. And you've also got the peak range around 2,850 to 3,090 reciprocal centimeters, characteristic of the alkanic kind of CH stretches. It is often termed a supporting analytical technique, as the only information it really provides relates to the presence or absence of certain chemical bonds associated with different functional groups and molecules. It provides little other structural information. However, it is a powerful technique in making some key decisions on the beginning of working out what a compound is. And usually it's a start for an organic chemist on this journey to determine what the compound would be. Okay, so here is a question for you. The infrared spectrum here of an unknown compound X of molecular formula C3H6O2 is as follows. Okay, I've only given you the infrared spectrum. So what I want you to do now is just pause the video and see if you can work out what bonds are responsible for the peaks at A, B, and C in the following spectrum of X. And then we'll go through the answers. Okay, so welcome back. So what you should have seen is that broad stretch around 3,000 reciprocal centimeters should be the OH. Then around 1,700 you have the carbonyl, and around 1,100 would be your CO stretches. Okay, so you can use your data booklet for this. So you should have used your data booklet to elucidate those particular values. Right, so proton nuclear magnetic resonance, or proton NMR, is the next technique we're going to look at. So proton NMR spectroscopy gives us information on the different chemical environments of hydrogen atoms in a molecule, and is possibly the most important structural technique available to an organic chemist. I use it a lot in my PhD. The nuclei of the hydrogen atom can exist in 2 possible spin states. As such, they can behave as tiny little magnets. When there is no magnetic field, the 2 spin states have the same energy and random orientation, and when the 2 nuclei are placed in a magnetic field, The spin states may align with the magnetic field or actually against it. This means that two energy levels exist. The parallel alignment of the nuclear spin with the external magnetic field is of a lower energy compared to the anti-parallel configuration, and this energy difference, delta E, corresponds to the radio wave region of the electromagnetic spectrum. As the applied magnetic field is increased, this change in energy will increase, and the energy difference depends on the different chemical environments of the hydrogen atoms. In proton NMR spectroscopy, the emission of the nuclear magnetic resonance signal relative to a standard, which is known as trimethylsilane or TMS, is termed the chemical shift. It is expressed as parts per million of the proton, and the chemical shift for TMS is given as 0. And hydrogen nuclei of different chemical environments have different chemical shifts, which you can see in section 27 of your data booklet. The number of signals in the proton NMR spectrum shows the number of different chemical environments in which the hydrogen atoms are found. For example, in the proton NMR of ethanol, 3 signals are found, which show the different chemical environments of the different hydrogens in the molecule. The 3 different types of hydrogen in the molecule: the methyl hydrogens, the ethyl hydrogens, and that final OH hydrogen. Another useful feature of proton NMR spectroscopy is that it contains an integration trace that shows the relative number of hydrogen atoms present. In this particular case, you'll see that that will integrate, so basically what you get on your trace, okay, so this is basically the area underneath the particular peak. Okay, so you'd see something like that. That would show as 1, the complete area. That would show as 2, and that would show as 3. An important application of proton NMR spectroscopy is associated with the fact that protons and water molecules within human cells can be detected by MRI, or magnetic resonance imaging, which gives 3-dimensional views of organs in the body. So, in terms of proton NMR spectra, here we go. Here's a proton NMR spectra of mystery compound X with a molecular formula C3H6O, which is shown as below, okay, with the integral, which is good. Deduce which of the following compounds X is and explain your answer. You can, of course, use your data booklet for the particular chemical shifts. Okay, so just pause the video now and see if you can get that correct. So what you should have got was the compound was CH3CH2CHO, so it's an 1,2,3 propanol. Okay, so only this compound would give 3 peaks because there's 3 different chemical environments. Only this compound has hydrogen atoms in 3 different chemical environments. Only this compound has protons in the ratio of 3:2 to 1, and only this compound will have a peak in the 9.4 to 10 ppm region of the hydrogen attached to the carbon, which is attached to the oxygen, the aldehyde. So the next thing we're going to look at is the index of hydrogen efficiency, which we'll link in with here. Okay, and the degree of unsaturation, or index of hydrogen deficiency, IHD, can be used to determine from a molecular formula the number of rings or multiple bonds in a molecule. The degree of unsaturation is used to calculate the number of rings and pi bonds present in the structure, where a double bond is counted as 1 degree of unsaturation, a triple bond is 2 degrees of unsaturation, a ring is counted as 1 degree of unsaturation, an aromatic ring is counted as 4 degrees of unsaturation. Now the IHD can be worked out in 2 ways, okay, from the structure and from the molecular formula. So there we have the structure itself, okay, so from the structure you can work out the IHD. The other way you can do it is from the molecular formula. So in order to deduce the IHD for a generic formula, it's given, where X is a halogen atom, either a fluorine, chlorine, bromine, or iodine, we use the following expression in red. For an IHD of alkanes to be 0, you need to make carbons equal to hydrogens. For this, you need to double the carbons and add 2. Therefore, 2C plus 2 minus H will give an alkane. Nitrogen adds hydrogens, therefore it's a plus N. And halogens reduce hydrogens, therefore it's a minus X. Losing a hydrogen and gaining something else has the effect of 2, so it's all divided by 0.5, therefore we get the equation. So just to reinforce the learning, determine the IHD for C6H6. So pause the video now and then come back when you think you have an answer. Right, so the IHD is plug the numbers in. Okay, so it'll be C6, okay, so plus, minus 2 minus 6. Okay, so it will be 4. The possible solution of this compound C6 could be any of the following structures. We don't really know yet until we verify with proton NMR or infrared spectroscopy or mass spectroscopy, which is our next topic. Okay, so finally we'll look at mass spectroscopy. When a gaseous molecule is ionized, its molecular ion M+ is formed. The molecular ion peak in a mass spectrum corresponds to the molecular mass of the compound. Owing to the high energetic ionization process involved in the mass spectrometer, the molecule can in fact break up into smaller fragments. That's the whole principle of mass spectroscopy. Some of this will be ions. The fragmentation pattern observed in mass spectrum provides further information on certain functional groups present in the molecule. Section 28 in your data booklet lists the number of these fragments and their associated masses, which can be used to reconstruct what molecule you've ended up with. So here, for example, is the mass spectroscopy or mass spectrum for ethanol. Okay, so you see a nice peak at 15, which is the methyl group, which is broken off. There you go. Got the 17, which is your OH group, which is broken off. We have the 29, which is the C2H5, which is broken off, that whole thing there. And we also have the molecular ion of 46. So just to finish, let's just have the IR spectrum, well actually only the mass spectrum is given in this example, of mystery compound X. Seems that we don't know what compound X is quite a lot, of a molecular formula C3H6O2, it's given. In the mass spectrum of X, deduce the ions with the MZ values of 74, 45, and 29. Now remember, M is mass and Z is going to be charge. So what's 74, 45, and 29? Pause the video now. You can use your data booklet, of course, and see if you can actually work it out. Okay, so what you should have got was the 74 was the parent ion positively charged. MZ45 is the carboxyl group positively charged with a proton on it, and then the ethyl group with a positively charged. So that is the answer for that. So that's the SL component of spectroscopy. So you've now got a bit of a feel for both mass spectroscopy, proton NMR, and infrared spectroscopy. And now in the next lesson, we're going to delve deeper with the HL component, which gives it a little bit more complexity.